Welcome, cosmic explorers, to a breathtaking journey through the universe. Today, we're diving deep into the incredible life cycle of stars, from their mysterious birth in vast clouds to their explosive deaths as supernovae. Stars are the heartbeat of the cosmos, forging the elements of life, lighting up the night sky, and shaping the galaxies we marvel at. How do these brilliant beacons form? What fuels their fiery lives? And what spectacular fates await them? Buckle up, because we're about to embark on an epic adventure that will stretch your imagination and leave you hungry for more. Let's unravel the life cycle of stars together. Picture the universe, a vast expanse dotted with galaxies, each a swirling dance of stars. These celestial giants are more than just twinkling lights, they're cosmic engines, born from chaos, living for millions or billions of years, and dying in ways that reshape the cosmos. Every star has a story, a life cycle driven by gravity, heat, and nuclear fire. From the humblest dwarfs to the mightiest giants, stars create the elements in your body: carbon, oxygen, iron, and seed the universe for new worlds. The journey from birth to supernova is a tale of beauty, power, and mystery. Doesn't that make you wonder how a star's life begins? Let's start at the cradle of stars, their birth. Stars begin in nebulae, vast clouds of gas, mostly hydrogen, about 74%, and helium, around 24%, mixed with traces of dust. These cosmic nurseries, like the Orion Nebula, span light years and shimmer with potential. Gravity, the universe's sculptor, pulls clumps of gas and dust together, forming dense pockets. As these clumps collapse, they spin faster, like a skater pulling in their arms, and heat up from the pressure. Temperature and density rise, and a protostar forms, a hot, glowing core shrouded in a dusty cocoon. This stage can last thousands to millions of years, depending on the mass. The bigger the clump, the more massive the star to be. Isn't it amazing to think a cloud could birth a blazing star? The protostar's journey isn't guaranteed. It needs enough mass to ignite the fire of life. As the core collapses, temperatures soar, reaching millions of degrees. At around 10 million Kelvin, hydrogen atoms smash together, fusing into helium. This nuclear fusion releases tremendous energy, a glow that pushes back against gravity's crush. When this outward force balances gravity, a star is born, entering the main sequence phase, the longest chapter of its life. Our Sun, a middleweight star, has shone for 4.6 billion years and will for another 5 billion, fusing hydrogen steadily. This balance is the secret to a star's stability. Can you imagine the power brewing in that fiery core? The main sequence is a star's adulthood, and it's all about mass. Stars come in a wild range, from tiny red dwarfs, just 0.08 times the Sun's mass, to massive giants, 50 or even 100 times heavier. Mass dictates everything. How bright a star shines, how long it lives, and how it dies. Low-mass stars, like red dwarfs, burn slowly, sipping hydrogen, and can live trillions of years, outlasting the universe's current age of 13.8 billion years. Our Sun, a G-type star, burns at a moderate pace, shining yellow and steady. Massive stars, like blue giants, guzzle fuel fast, blazing millions of times brighter but lasting only millions of years. The Hertzsprung-Russell diagram, a stellar map, plots this, showing temperature against brightness. Isn't it wild how a star's size shapes its destiny? Let's dive into fusion, the heart of a star's life. In the core, extreme heat and pressure strip hydrogen atoms into protons, which collide and fuse. In a process called the proton-proton chain, dominant in stars like the Sun, for protons combine, step by step, to form helium, releasing energy as light and heat. For massive stars, the CNO cycle, carbon, nitrogen, oxygen cycle, kicks in, using these elements as catalysts to fuse hydrogen faster. This energy, born of Einstein's E equals mc squared, powers the star, balancing gravity's pull. A single gram of hydrogen fusion releases energy like burning tons of coal. The Sun converts 600 million tons of hydrogen to helium every second, a cosmic furnace lighting our days. How incredible is that engine? During the main sequence, stars are stable, but change looms. As hydrogen runs low, the core shrinks, gravity squeezing it tighter. This heats the core, speeding fusion, while the outer layers swell, cooling and reddening. For a star like the Sun, this marks the shift to the red giant phase. The core, now hotter, fuses helium into carbon and oxygen, a new trick needing 100 million degrees. The Sun will swell, perhaps engulfing Earth, in about 5 billion years, glowing red and huge. For low-mass stars, this phase is gentle, lasting billions of years. Massive stars rush through, becoming red supergiants, like Betelgeuse, bloating hundreds of times wider than the Sun. Doesn't that dramatic transformation spark your curiosity? Let's explore the red giant phase for stars like the Sun. With hydrogen depleted, the core contracts, and the shell of hydrogen around it keeps fusing, puffing up the star. Helium fusion begins in the core, producing carbon and oxygen, while the star's surface cools to 3000 or 4000 Kelvin, turning red. This phase lasts about 1 billion years for the Sun. The star sheds mass, blowing gentle winds of gas and dust, enriching space. Inside, the core builds heavier elements, but not past oxygen for stars this size. The outer layers billow out, unstable, pulsing with light. It's a grand, aging dance, setting the stage for the end. Can you picture our Sun as a bloated, red giant? For massive stars, the story accelerates. Red supergiants, 8 to 50 times the Sun's mass, burn hot and fast. After hydrogen fuses to helium, helium fuses to carbon and oxygen, then carbon burns to neon, magnesium, and more. Each stage is shorter, hotter, needing billions of degrees. In the core, a layered onion forms, an iron core, surrounded by shells of silicon, oxygen, carbon, helium, and hydrogen, all fusing at once. Iron's the limit, fusing it consumes energy, not releases it. This takes millions, then thousands, then mere days for the heaviest elements. The core grows massive, unstable, teetering on collapse. The stage is set for a cosmic spectacle. Now, let's follow low-mass stars, those under 8 solar masses, to their quiet end. After the red giant phase, the core, rich in carbon and oxygen, can't fuse further. Gravity squeezes it, but not enough for more fire. The star sheds its outer layers, puffing them off in a glowing cloud called a planetary nebula, misnamed, as it's not a planet. The Eagle Nebula's pillars of creation show this, birthing new stars too. The core, Left behind, collapses to a white dwarf, a dense, Earth-sized ball, a teaspoon of which weighs tons. No fusion now, it glows from leftover heat, cooling over trillions of years to a dark, cold black dwarf. Our sun's fate is this gentle fade. Isn't that a poetic end? Massive stars, though, go out with a bang. When the iron core grows to about 1.4 solar masses, the Chandrasekhar limit, it can't hold. Electrons and protons smash together, forming neutrons and neutrinos, and the core collapses in a fraction of a second, from Earth-sized to a 10-kilometer ball. The outer layers crash in, rebound off this dense core, and explode in a supernova, one of the universe's most dazzling events. A single supernova outshines a galaxy, blasting light, heat, and elements, gold, silver, iron, into space. Supernova 1987A, seen in 1987, wowed us, confirming theories. The core becomes a neutron star, incredibly dense, or, if massive enough, a black hole. What an explosive finale! Let's linger on supernovae, because they're cosmic game-changers. Two types exist, Type Ia, from white dwarfs in binary systems, and Type II, from massive stars. In a Type Ia, a white dwarf sips mass from a companion, hits the Chandrasekhar limit, and detonates, a standard brightness helping us measure cosmic distances. Type II, from massive stars, follows the core collapse we described, blasting shock waves and neutrinos, ghostly particles flooding out. Supernovae seed the universe with heavy elements, forged in stars and scattered in these blasts. Your body's iron, from blood to bones, came from such explosions. They trigger new star birth too, compressing nebulae. Isn't that a stunning legacy? Neutron stars, born from supernovae, fascinate us. These remnants, 1.4 to 3 solar masses, collapse to a tiny, dense core of mostly neutrons. A sugar cube of neutron star weighs 1 billion tons. They spin fast, some hundreds of times a second, and strong magnetic fields beam radiation, creating pulsars. In 1967, Jocelyn Bell Burnell discovered the first pulsar, its regular pulses like a cosmic lighthouse. If the core's mass exceeds 3 solar masses, gravity wins, collapsing it past a point of no return, forming a black hole. Here, gravity warps spacetime, trapping even light. These fates dazzle us, don't they? Let's explore the cosmic impact. Stars, through their lives, fuse elements, hydrogen to helium, then carbon, oxygen, and beyond in massive stars. Supernovae blast these into space, enriching nebulae for new stars and planets. Earth's carbon, oxygen, even gold in your jewelry, trace to ancient stars. The cycle connects the universe, a star dies, its debris seeds a nebula, and new stars ignite. Galaxies grow, shaped by this dance. Observations, like the Crab Nebula, a supernova remnant from 1054 AD, show this live. Stars aren't just lights, they're the universe's builders. How does that tie you to the cosmos? Tools fuel this quest. Telescopes, from optical ones like Hubble to radio dishes, catch starlight across the spectrum. Spectrographs split light, revealing fusion's fingerprints, hydrogen, helium, and more. X-ray telescopes, like Chandra, probe supernova remnants and neutron stars. Neutrino detectors, buried underground, snag particles from core collapse. Computer models simulate star birth, life, and death, matching data from the Orion Nebula to Betelgeuse. Each advance deepens our view, unveiling the cycle. What new tech will light the way? Challenges abound. Nebulae are vast, obscuring protostars in dust. Fusion hides deep in cores, beyond direct view. Supernovae are rare, centuries apart in one galaxy, needing luck to catch. Black holes evade sight, revealed only by gravity or jets. Yet, scientists innovate, combining light, neutrinos, and gravitational waves, ripples from star collapses detected by LIGO since 2015. Each hurdle sparks brilliance, pushing us to learn. The universe tests us, doesn't it? Let's bust myths. Stars don't burn like fire, fusion, not combustion, powers them. Not all end in supernovae, only massive ones do, while most, like the sun, fade quietly. They're not eternal, lives range from millions to trillions of years. And no, supernovae don't destroy the universe, they build it, seeding elements and stars. The real story, from birth to explosive end, outshines fiction, blending physics, beauty, and wonder. What surprises you most? The future dazzles. The James Webb Space Telescope peers into nebulae, spying baby stars. The Vera C. Rubin Observatory maps the sky, tracking supernovae. Gravitational wave detectors hunt stellar collisions. We'll probe fusion, map remnants, and predict deaths. Betelgeuse might blow soon, in cosmic terms. Could we catch a star's final breath live? Might we learn how elements form? The cycle unfolds, and we're watching. What does this mean for us? Stars forged your atoms, from breath to bones, linking you to the cosmos. Their cycle, birth in nebulae, life in fusion, death as white dwarfs, neutron stars, or black holes, drives the universe's story. We gaze, wonder, and study, from ancient sky watchers to modern telescopes. This quest, fueled by curiosity, ties us to eternity. You're stardust, alive in a cosmic tale. As we near the end, let's gaze ahead. The life cycle of stars reveals creation, power, and rebirth. New tools, data, and theories will deepen this saga, from protostars to supernovae. What secrets hide in nebulae? How will the next blast light the sky? The universe beckons, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into the life cycle of stars, from birth to supernova. I hope your curiosity blazes. If you love this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about stars? What mystery should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Explorers.